Alright, as promised, the last video of this chapter is on real gases. And real gas is just what it sounds like. It's an actual real gas. So let's just first look at what we call the van der Waals equation. Van der Waals equation. It was named after a Dutch physicist, Van der Waals. So the equation is P plus A times n squared over V squared times, okay, I'm just going to fix that so it doesn't bother me, V minus N times B is equal to nRT. So hopefully you can look at this and realize that it's basically just the gas law, ideal gas law. PV equal to nRT. I'm not going to go into great detail as to what all of it means, but basically this term right here, that corrects for what we call intermolecular forces. So some gases attract each other, some repel. Those are intermolecular forces. Remember, that's one of the things about the kinetic molecular theories. They don't attract or repel each other. So that adds a little bit to the pressure, that term there that I've circled in green. And this term here corrects for particle volume. So again, one of the things about KMT is the particles are small compared to the gas itself. That's not always true. Actually, it's never true. It just depends on how big or small the gas is, how much that is true. And N on both sides is just number of moles. We're not going to do calculations with this, so you don't really need to worry about how to do the calcs. And A and B are just constants. For a particular gas. So if they're just constants, we just look them up. And every gas has its own set of A's and B's. I just wanted to look. And in order to kind of understand this a little bit further, I just want to say that gases behave more ideally at high temperature and low pressure. Basically, both those conditions keep the molecules away from each other. High temperature, the molecules zoom right past each other when they collide. They don't kind of stick to each other, as it were, which is what an intermolecular force does. The collisions are so fast that they just kind of bounce right off of each other. And at low pressure, the molecules are much less likely to encounter each other. So that also is key. So any gas will behave more ideally at high temperature and low pressure. So let's just look really quickly at a series of gases, and let's look at their molar volume. At SPP. And we'll kind of use this just to kind of gauge how ideal each gas is. So we'll just list the gas here, and then its molar volume. And that'll be in liters. Okay. So just list an ideal gas first. An ideal gas, use the PV equals nRT, and we get 22.41 liters per mole. Oops. Molar volume, that should be liters per mole. And then if we look at Cl2, its molar volume is 22.06. So that was one of the least ideal gases on the list. CO2, and these are relatively small differences, but they can make a big difference depending on what you're doing. 22.31 for CO2. NH3, ammonia gas, 22.40, pretty close to ideal.